Now we're going to take a look at the other part of the fundamental theorem of calculus. It's often referred to as part 2, or the second part of the fundamental theorem of calculus. The first part, remember, said we can find the exact area trapped in the plane using the antiderivative at the upper limit minus the antiderivative at the lower limit. Well, for the second part of fundamental theorem, we're working with a type of function that is a function defined to be that accumulated area in the plane, starting at some constant real number value of a and stopping at some value that they tell us to stop at, which they're calling here x. So this really is the accumulation function, and we'll see as this develops that this is the accumulation function that we referred to as accumulating area in the plane over an interval for fundamental theorem part 1. So let's take a look at it. If f is continuous on a closed interval a up to b, then the function big F of x is the antiderivative, or the function that is the accumulated area in the plane between little f over the interval from a up to x, and has a derivative at every point on the closed interval. And specifically, its derivative looks like this. If I have a function defined as an integral and I'm going to take the derivative of that function, whatever I do on one side of the equal sign, I've got to do the same thing on the other side of the equal sign. So you can see in this step right here, all I've done is take this function defined as an integral, and now I am going to take the derivative of the integral. Remember, we said before that these two operations are inverse operations, meaning they undo each other, and we've seen that in our work in differentiation and integration. If we start at f and we want to find f prime, we differentiate. If we start at f prime and we want to find f, we integrate. So these two operations undo each other. So we use the chain rule when we start talking about taking the derivative of a function under fundamental theorem of calculus part 2. So let's walk through the chain rule, and you'll see, and this is one of the reasons why I have verbalized the chain rule the way that I have, because here is a function that looks very different from some of the functions that we have been differentiating. So we want the derivative of this function. So here is the outside function. This is the outside function. F of t is outside. There's our outside function, and this will always work for us. The upper limit, which is a variable, and we'll see it can be a function as well, is the inside. So the upper limit, whatever's in the upper limit, is the inside for us. So we want the derivative of the outside, which is right here, not changing the inside, there's the inside, right, times the derivative of what's inside. Well, the derivative of x is 1. So, in essence, what we get, especially when our upper limit is just this same variable, whatever that variable is, if it's all that's up there, then in essence what we get from the notation that we have is just a variable change. Right? Those two operations are undoing each other. We want the derivative function in terms of x. We're differentiating with respect to x, so our answer should be given in terms of x. So as we do some examples, if this is just a little bit shaky for you right now, as we see several examples, it'll become more and more and more clear what fundamental theorem of calculus part 2 is actually doing. So again, if we have a function, we started out with big F of x, was the accumulated area in the plane from a, which is a real number, a constant, up to x, which is a variable, of f of t dt. If we are going to differentiate this function, then we are undoing the integration operation with differentiation. And basically, in essence, what we get, especially when our upper limit looks like this, is we just get a variable change. Whatever this function looks like, everywhere this function has a t, this function is going to have an x. And this is a definite integral. Notice there is no plus c out here, right? All right, so basically what we have, another way to look at this, is here's fundamental theorem part 1. Do you agree? If we have a definite integral, then fundamental theorem part 1 says the exact area accumulated in the plane from a up to x is the antiderivative at the upper limit minus the antiderivative at the lower limit. Well, if we differentiate that, this, if we plug a into the antiderivative function, this is a constant. The whole thing, big F of a, not just a, but big F of a is a constant. So when we take the derivative of a constant, we get 0. All right? And the derivative of the antiderivative maps us back to where we started. So in essence, that's why it just feels like we get a variable change from this function. Let's do this example. Here is a specific example. We have big F of x that was defined as the accumulated area in the plane starting at 0, a constant, and stopping at x underneath this function 1 over 1 plus t squared dt. And so we want f prime of x. So that's the chain rule. Remember, here's outside, here's inside. So what that's going to look like is it is the derivative, right, of the outside. I'm going to take the derivative of the outside, which looks like this, not changing the inside. The inside is x, right, times the derivative of what's inside. So basically what I wind up with is 1 over the quantity 1 plus x squared. Here's your function in t, and what I get is the same function, except everywhere this one has a t, this one has an x. And that is the function f, right? If we define this to be f of t, like we've done, it is the derivative function in x. So there's what fundamental theorem of calculus part 2 gives us. Here's another example. Here I'm not using big F, I'm using big A. It doesn't matter. We're not going to get real attached to any one notation. It is true that the accepted or most common notation you're going to see here in a function defined as an integral is the letter t. But understand, it could be any letter. It doesn't have to be t. It's just got to be some letter other than what that variable is. The reason why this is not f of x dx is because I'm accumulating up to some x. So this has got to be some letter other than what the function is defined to be in. So this is just, we call this a dummy variable. Okay, so from everything that we've seen so far, if I want the derivative of this function, and the chain rule, right, is going to say that the derivative of what's inside is times 1, then in essence what I'm going to get is I'm going to get that function f of t, and I'm going to write it in terms of x. So here is another exact example. There are some things we need to make sure of. We need to make sure that we are taking the derivative of an integral. So we need to make sure that our function is defined as an integral. And we need to make sure that we have an upper limit that is a variable and a lower limit that is a constant. Then we can apply fundamental theorem part 2. So fundamental theorem part 2 says, again, here's outside, right? And here's inside. So this is outside in our terminology, and this is inside when we do our chain rule. So I want the derivative of the outside, which means I just copy down everything that's going on in f of t, and I put parentheses where there's a t, because there's the derivative of the outside. Not changing the inside. Everywhere there's a t, I put an x. And then times the derivative of what's inside. Well, here's inside. And with respect to x, the derivative of x is 1. So in essence, a prime of x is the cubed root of x to the 4th plus 5x. How simple is that? Very simple. All right, here's one where the power and the reason we're using the chain rule will become evident. Here, I want to write this bigger so you can see it. Here we have a function. I'm no longer using big and big letters and little letters and all that kind of stuff. I can define a function as an integral anytime I want to, and I can call that function anything I want to. So g of x is defined to be the accumulated area in the plane starting at 0 and stopping at x squared between the function cosine and its horizontal axis. Again, t is a dummy variable. When they ask me to take the derivative of a function defined as an integral, then they are putting me in the context of fundamental theorem part 2. And what that looks like is it's the derivative of the outside, which means I copy down the function and put parentheses everywhere there's a t. Not changing the inside. Remember, your upper limit is the inside. Well, now my inside is not x, my inside is x squared. So not changing the inside, right, chain rule, now times the derivative of what's inside. So 2x instead of what we normally have been putting is 1. The chain rule is definitely going to come into play when we have some other function up here. So this cleans up to 2x times the cosine of x squared. And that is g prime of x. Okay, another example. Here, we don't have all the players like they're supposed to be. If we have a function defined as an integral, let's call this h of x. This would be h of x, so this would be h prime of x, right? So what we need is we always need the lower limit to be a constant. And we've been calling that constant a. And we always need the upper limit to be the variable limit, the limit that has the variable in it. We have to have that case before, we have to have this being true before we can use fundamental theorem part 2. And you can see here, that's not what we have. We have the lower limit as our variable and the upper limit as our constant. So that's an issue. Do we know how to fix that? Do you remember that there is a property of the definite integral that says I can pop a negative out front and I can reverse the limits of integration? Do you remember that? We have a property that's going to allow us to just change the way this function looks without changing its value, right? The function defined as an integral. Now I can apply fundamental theorem. I put my negative down, taking the derivative of an integral. It is the derivative of the outside, not changing the inside, times the derivative of what's inside. Not changing the inside times the derivative of what's inside. We normally don't write times 1, but there it is. So the derivative, h prime of x, is negative 3x times the sine of x. Let's see. We'll stop there and we'll pick up. I've got some more examples to do. We'll do them in the next video.